All right, so if I remember correctly, there's mastering due tonight, right? Mastering? Good, good, good. My brain has not completely fallen apart. So I know this is going to make everybody sad, but we're going to have to end class early. Don't worry, we're still going to have time for the quiz. It's because the biology seminar about dolphins is in here at 1 o'clock, and it's cultural events credit.
Do we get extra credit if we go?
Yes. That could double count CE credit and extra credit. Yeah. For it to count as the extra credit for me, you have to write a 1-paragraph summary, which means at least 3 sentences. One of which cannot be the title of the talk. Has to be 3 additional sentences. And then that count, and then email it to me. Ask away.
I'm trying to drop the class to I'm not in right now. And we've only got the lab.
You have to wait for me to authorize you, and then they can show you how to switch it.
Okay.
What I did, I just did a couple minutes and I did like a little thing on top of like switch
All right. I think I'm mostly mentally ready to talk about heat capacity. This is not going to be my best lecture. Throwing it out there. This is not going to be my A game. I'm going to do my best. All right, does everyone have a calculator with them today? Yes, I would fish that out. We will be doing some calculating with a calculator. Group. All right, so last time we talked about heat, energy, work, Q's, W's, delta E's. All sounds vaguely familiar. Good? No. No, because you need to flip back a page and check that real quick. Because you'll need that information in your head for the quiz. So when a system absorbs heat, its temperature changes by delta T. That should make sense, right? So in words, again, heat absorbed is proportional to the temperature change. Which mathematically we could write as heat is equal to the change in temperature times a constant. Where C is heat capacity. So heat capacity is the amount of heat or quantity of heat required to raise the temperature by 1 degree Celsius. So guesses as to what the units of temperature should be in. They need to be in Celsius. So unlike everything we just did in gas laws, we are now going to be only in Celsius for heat capacity. Because I wanted to be as tricky as possible. I wanted to make sure that it seemed impossible to do the problems. All right, so temperature is now going to be measured in change in Celsius. C is in joules per degree Celsius. Heat capacity is also an extensive property. We talked about this weeks and weeks and weeks and weeks and weeks and weeks ago, like in week 1, the difference between extrinsic and intrinsic property. In case you have forgotten, which I can't imagine this piece of knowledge would have escaped your brain in any kind of way. An extensive property depends on the amount of thing that you're measuring. So heat capacity is going to be dependent on the volume or amount of typically water that you have to measure. So then we also have specific heat capacity. This is the quantity of heat required to raise the temperature of 1 gram of material by 1 degree Celsius. Specific heat capacity has the units of joules per gram degree Celsius. So our equation for that, let's see if I can fit it all down here. So heat can also be mass times specific heat capacity times change in temperature. Oh, that's hard to see. That's a bit better. So heat is equal to mass times specific heat capacity times change in temperature, where the specific heat capacity is an intrinsic property. Depends on the kind of material, not the amount of material. Okay, there. Questions so far on our definitions? Okay. Here we have specific heat capacities of a variety of materials. This table's in your book, so don't feel like you have to write it down. But of these materials, which has the largest specific heat capacity? There's one real obvious one. Oh, one higher than that. Water. Which we experience all the time, you probably just don't think about it. So water requires a lot of heat to change the temperature. So for example, you can think about swimming in the pool, right? You're getting in the pool, and you're usually getting the shallow end. And then if you're anyone else on the planet, you'd actually make your way to the deep end. I'm very happy just in the shallow end, just about waist high. We're good there. But if you swim towards the deeper end, what happens to the temperature of the pool, typically? It gets colder, because the same amount of energy that made the shallow end fairly warm is not enough to make all that water warm. So if you try to have a heated pool, you're really trying to heat it so that the deep end of the pool is warm and the shallow end is just hot, I guess, at that point. So let's do a math example that puts together some of that knowledge. So let's say, for example, you are going to start your own Etsy business. For the 5 of you that know what Etsy is. your new craft idea is going to be making stained glass. So given that glass turns to a liquid around 1500 degrees, and you are starting at room temperature, how much heat does a 2.5 gram piece of glass absorb? So I have given you, right, heat. What letter is heat? Q. So I'm looking for Q. And I gave you a mass, so we're going to use this one. All right, so looking at your previous one where I had the table, what's the value of specific heat for glass? Yep, right there, 175. Okay, good. So our mass was 2.50 grams. Our specific heat was 0.75 joules per gram degree Celsius. Then what is our change in heat? 1500 minus 25. So let's double check and see how much heat that would absorb. How many significant figures do I get to have? 2. We'll make it 3 because 2 doesn't mean very much. We'll tell it that. We'll do 3. That's a surprising amount of heat. That's a lot of joules. A lot of joules. So you'd have to have a pretty hot oven to start turning your glass into a liquid, pliable liquid. Questions on that really tricky math? Everybody see where I got the numbers to plug it in? Good. Just checking. Alright, so that is all awesome. Assuming we're at 1 atmosphere, our volume hasn't changed. What if we do have a changing volume? I'm sure you guys were all thinking that. Like, this is all great, but what happens if the volume changes? Don't worry, we'll cover it. So how does work change when the volume changes? Here's my example, our thought example. A car engine. Is that spelled right? Yeah, that's right. It looks funny. All right, I know 0 about cars, but I know this one thing about how combustion works in a car. And I know it needs gas, and you're supposed to take it and have it fixed every now and then. It has tires and stuff, but I think everyone would agree that, right, a regular combustion equation, you have gas, you heat it up, makes water and carbon dioxide. Do you have carbon dioxide before? No. Right, this is our typical equation. And what states of matter is that carbon dioxide and water typically in? They are typically gases. So what has happened to the volume of my reaction? I had liquid gas, right, liquid methane. I've heated it. Now I have gases. Everyone in your head all at once, it's expanding, right? I have way more volume than I had before. Good. All right, this reaction takes up volume, and that change in volume actually is the thing that makes your piston go up. So this reaction, your methane turning into a gas, forces that piston to move because the gases take up more space. And so the piston's movable, gets out of the way. And then when all the gas has disappeared, it lowers again. That's the one thing I know about engines. That's it. I'm not exactly sure where the pistons are in there. I could probably point them out. I could probably figure it out. I think it's in the middle. I know where the battery is. I know where the gas goes in. And the windshield wiper fluid. I know where that goes. Not to be confused with the gas. That's about it. So, how do we rearrange our work equation to take account for this? This is our new work equation. So work is equal to negative pressure change in volume. If the volume is changing, what is this saying about the pressure? Is the pressure changing or is it a constant? Volume's changing because I put a big delta in front of it. Did I put a delta in front of the P? So if there's no delta, it has to be constant. So the other question may be, well, why is there a negative sign? It's kind of weird to have negative work. Okay, so work is negative because work is being done on surroundings by the system. So, going back to my engine example, right? My system was this reaction, right? Methane turning into two gases. That system is then doing work on the piston. So the piston's being worked upon, but the loss, like the negative value is for the system. So this has a negative value because it's losing work because it's doing the work on somebody else. Does that maybe make more sense? I appreciate the sympathy nods. Good, thank you. Thank you. I figure if I wait long enough, at least one person will be like, yes, just move on. Totally got it. Come on. All right, so then let's do a math example to put that thought into practice. So inflating a balloon requires pressure volume work. So if I inflate the balloon from 0.2 liters to 0.985 liters in this room, where it has an external pressure of 1 atmosphere, how much work in liter atmospheres has been done? So we're going to use the equation we just used. So what is the pressure for this problem? 1. How do I calculate the change in volume? Do a subtraction. Do I subtract 2 from 0.2 from 0.9? Which one's the final volume? 0.9. So you do that first. Let's see what that turns out to be. How many significant figures do I get? So the work is negative 0.785 liter atmospheres. Okay, so if I'm blowing up the balloon, and that's my activity, and it's negative, what is considered the surroundings? The surroundings would be gaining work. What is the surroundings of the balloon? The air. So you are doing work on the air, you are forcing it out of the way. right? Because my balloon is getting bigger, which means the molecules you can't see in the air are being forced out of the way. Okay? Liter atmospheres is a real weird unit in terms of work. Like when you think of work, you typically think joules, energy. So 1 liter atmosphere is worth 101.3 joules. So how would I convert this value to this new value? I'll get us started. See, super helpful. How do I then finish this conversion? Do I put the 101 on top or on the bottom? I would probably put it on the top. Good there. I haven't made any mistakes so far. Good. Questions about constant pressure changing volume work. So, you may be thinking, but there's definitely times when I'm holding my stuff all in one container, my volume's a constant, but I'm putting more molecules in there. If you're putting more molecules into this one beaker that has a lid on it, what's happening on the inside? What's changing? Pressure. We now have constant volume calorimetry, which you'll be doing in lab this coming week. Constant volume calorimetry with the coffee cups and everything. So, if we want to measure delta E, we're going to have to look at constant volume. So here's what we've all done. We've done system and surroundings. If I'm looking at just the heat component, right, Q is mass times specific heat times temperature. That should really be change in temperature. So the heat can either go system surroundings or surroundings to systems. Either one's fine. If I want to know about the work is negative P delta V. I could do work on the surroundings, or the surroundings could do work on the system. And we also know that the overall change in energy is however much heat and work has been done total. So if I want to know for an overall system, right, I was looking at the same combustion system I was just looking at, and I want to know the overall change in E for that system, I could do a bunch of little experiments, right? I could vary the temperature, get a whole bunch of heat measurements, then keep it at one temperature, change all the volumes, get a different set of work, then add them together and find out the delta E of the whole system. Or more often we hold volume constant. If I hold the volume constant and measure the temperature change, am I measuring heat or work? If I'm looking at change in T, I'm looking at heat. If I am at constant volume, what is my delta volume? 0. Now that's your question. 0. if I'm at constant volume where V equals 0, what then does W equal? 0. If W equals 0, what's my change in energy equal to? So at constant volume, the change in energy is only due to the change in temperature, heat. So it's a workaround to figure out the change in energy of a system. If I can hold half this constant, right, if E equals Q plus W, if I can hold the volume constant, then delta E is only equal to Q. It's a good workaround to figure out the delta E of an entire system. Oh, sneaky scientists. So, let's then look some more at this calorimetry idea. So, any ideas of what units calorimetry measures in? Calories. Good. Calories are directly related to joules. So we'll do most of our measurement in joules, but be thinking, oh, calorimetry means delta E, because delta E is measured in joules. So calorimetry is a way to measure changes in thermal energy. What does it mean, change in thermal energy? What is that? Temperature. You're thinking about that. Calorimetry measures changes in temperature between a system and its surroundings. At a constant volume, the change in temperature is related to the heat absorbed by the calorimeter. So, mathematically, we would state it like this. Right, we had this equation probably 15 minutes ago, right, where heat equals C times delta T. And this C was the heat capacity. So far so good. So the heat of calorimeter is the heat capacity of the calorimeter times whatever change in temperature the calorimeter is measuring. To make our math easier, we make a gigantic, incredibly wrong assumption that no heat escapes, that all the heat generated is directly measured by the thermometer. That's not heating the actual calorimeter, it's not heating the air, it's not turning into a different form of energy, that every single little bit of energy is a change in T. Really terrible assumption. But we can make it work. So, at least for Gen Chem. For Gen Chem is a terrible assumption. For Gen Chem is a great assumption, I guess. For regular chemistry. Not good assumption. But that's alright, you're only in Gen Chem, so it doesn't matter. So what we really say is that the heat of the calorimeter, which is the heat gained by the calorimeter, is equal and opposite to the heat lost by the reaction. So the calorimeter is our system, it's our surroundings, the reaction is our system, so it has to be equal and opposite. And that's all equal to the change in energy the reaction had. All right, we'll do one practice problem, and then we'll do our quiz, and then we'll all get out of here early. Unless you're staying for the dolphin lecture, in which case you're here early for the lecture. You got a good seat. All right, so let's say I have 2.09 grams of sucrose combusted, and the temperature of my experiment rose from 23.89 degrees to 28.45 degrees. First part is what is the delta E of this reaction? So we're going to use the equation I just wrote. Did I give you the heat capacity of the calorimeter yet? Is it in there anywhere? Nope. So I'll write that over here. Okay, it's 4.9 kilojoules per degree Celsius. So we can plug that in. And then what is our change in temperature? Let's see, 28 minus 23. How many significant figures do I get in my final answer? 3. Where are the units of my heat in this case? Kilojoules. All right, so that's Q at the calorimeter. But I want to know delta E of the reaction. So how do I go from Q cal to delta E? Equal and opposite. So it's the same value, just the opposite sign, because I'm saying the calorimeter gained this much heat, which means the reaction lost that much heat. Because we're all net zero. Okay. So then the last part of this is, what is this now in kilojoules per mole? Which apparently is the tricky question I ask on every exam, and everyone's like, I don't know what she meant. We'll do it all together, and we'll figure it out. All right. So that's part 1. This is part 2. All right, so far everyone agrees the delta E is negative 22.3 kilojoules. If I want to get per mole of sucrose, how do I use this piece of information about grams? I need to convert it to moles. So, this is part 2, continued over here. You wouldn't know this, but sucrose happens to weigh 342.3 grams. Off the top of my head, exactly 0.3. Yeah, I know you're close with your guessing. So 2.09 grams is right at 0.00611 moles. So how do I convert my kilojoules to kilojoules per mole? Divide it. Yay! That should be negative 0.62. What if I ask per atom? What would I do next? Yes. I would multiply by Avogadro's number, because that is molecules per mole. All right, we will pause there. If you want to move yourself into your